Okay, so imagine, if you will, if I were to take this thing here, this is a sensor which reads distance versus time. Imagine, if you will, if I were to pull this spring and let it go and let it bounce up and down like so. What kind of graph would I get? A sine graph? A cosine graph. Well, a sine graph and a cosine graph are really the same. There's just a phase shift of one or the other, correct?
Sinusoidal.
What's a sinusoidal wave?
It oscillates back and forth on a midline.
All right, it oscillates back and forth along the midline. Let's try it. All right, so I need a volunteer. Somebody come up and hit enter for me when I say go.
David's right there.
Because I can't hold the thing and push enter all at the same time. You ready?
Yep.
You hit enter?
Like right now?
Anytime. That's all you have to do. You may sit back down. Tough job.
Good job.
All right, so what kind of graph did I get, do you think?
It should have shrunk and like a cone should have shrunk down to a cone.
All right, so there's the graph I got. What can you tell me about it? It's wavy, it oscillates, but it's not really a sine graph. Why not?
It's like kind of gravity, air resistance, friction.
All right, so it's a sine wave, but it's decaying. The amplitude is shrinking as it goes. So this is what we call damped harmonic motion. Is the fancy words for it. Damped harmonic motion. Okay, so I want you to think about this for a minute. On my spring, here's my spring, and remember what I did? I stretched it out. What forces are acting on this spring? There's gravity, that's one force. There's friction, that's another force. There's the spring force. Okay?
You're forced to be pulling.
Well, what I meant was as soon as I let go, what forces are on it. So there's gravity, there's the spring constant, there's air resistance.
Your arm wavering.
My arm is wavering slightly. I tried to hold it very still. But I could, if I wanted to, I could put an external force on it and make my arm bounce up and down a little bit and keep it going, couldn't I?
Yeah.
So that could be another external force. Cheater, right. All right, so this is section 2.4. This is called mechanical vibrations. We consider a body of mass m attached to one end of an ordinary spring that resists compression as well as stretching. The other end of a spring is attached to a wall. So what they're considering in the book is that the spring is moving back and forth, left and right, across a frictionless surface. The one I did in demonstration, of course, moved up and down. But same thing happens. You get the same pattern. Let x be the distance of the body from its equilibrium position. What do I mean by equilibrium position?
This power is
If you just let it go and let it eventually come to a rest, it's going to stop somewhere, and that's called the equilibrium position, where the spring is neither stretched nor compressed. We take x greater than 0 when the spring is stretched, and x less than 0 when the spring is compressed. All right, so one of the forces that you told me that was acting on the spring was the spring force. And the spring force is governed by Hooke's law, which says the restorative force that the spring exerts on the mass is proportional to the distance x that the spring has been stretched or compressed. And so the restorative force, F sub s, is minus kx. Or k is a positive number. K is called the spring constant. Why is it negative kx? Because it's a restoring force. So if the string is stretched, I say that right? Spring, it's a spring. If the spring is stretched, then which way is the force going?
It's going back towards.
It's going in the opposite direction. So x would be positive if the thing is stretched out, but the restorative force would be going in the other direction, so it would be negative. Conversely, if the spring is compressed, then x is a negative number, but the restorative force would be
0 or
in the other direction.
0.
Oh, you're saying if you
If I've compressed the spring, correct. If I've compressed the spring, my x is negative, but the restorative force is going to be in the other direction. That will be positive. So that's why you have that negative in front there. The force is always in the opposite direction from where you are. Force due to a dash pop. The spring is oftentimes connected to a dash pop, better known as a shock absorber, that provides a force directed opposite of the instantaneous direction of the motion of the mass. We're going to assume the dash pot is designed so that the force is proportional to the velocity. And so again, we get the F sub r is minus CV, where C is some constant bigger than 0. And again, why is it negative? Because it's a restoring force. It's in the opposite direction. So if the velocity is currently positive, then what's the restoring force doing? It's in the opposite direction. It's going to slow it down. So that's why we have that negative there. Now, this dash pot could be part of your friction, could be part of your there was another force we talked about. What was the other one besides friction?
Gravity.
Gravity could be gravity. So you don't necessarily have to have it connected to something. It could just be natural. Wind resistance, gravity, so on and so forth. The constant C is the damping constant. More generally, we could regard this force as friction, air resistance, etc. If, in addition to F sub s and F sub r, the mass is subjected to a given external force, F sub e, then the total force of the mass is given by F sub s, which is the spring force, the resistance force, and the external force. So we add all of our forces together. All right, so we're almost ready for a differential equation. Here it comes. We now use Newton's second law of motion. F equals ma. So we add up our three forces, spring, resistance, external, and we get mass times x double prime. What's x double prime? Acceleration. That's the second derivative of position. But you might remember, looking back, that F sub s, that was opposite from position, and F sub r was proportional to the velocity, which is of course the first derivative, and then we had this external force. So we're going to move this kx and this cx prime over to the other side, and we get a second order differential equation with constant coefficients. M is mass, C is a constant, K is a constant, but it's not homogeneous, is it?
Nope. It's
Oh.
it's not homogeneous.
All right, so in this section, we're going to assume that we have unforced motion. What do we mean by unforced motion?
Perfect world.
No, not a perfect world. We're going to assume that when that spring bounced up and down, I was able to hold my hand perfectly still, and there is no external force. And that's called unforced motion, when you have no external force.
And this would make later on section 2.4 or 2.5 where we actually don't see zero.
After we finish section 2.5, in section 2.5 we will learn how to solve non-homogeneous equations. So we'll cycle back to this and we'll talk about what happens if you have an external force. So a couple words, we use damped and undamped motion, free and forced motion. If there is no dash pot, so if there's absolutely no resistance at all, we call that undamped. If C is positive, then the motion is called damped. If there is no external force, in other words, if f of t equals 0, the motion is called free. Otherwise, it's called forced. Now, of course, we could also consider the situation where we do have an external force, but it's exactly enough to balance off the dash pot. So what would happen in the case where we had an external force that was exactly enough to balance off the dash pot?
Equation would sum to 0.
What's that?
The equation would sum to 0.
Well, the equation wouldn't sum to 0.
The forces.
Well, these two forces here, this one and this one, would sum to 0. So we would end up with mx double prime plus kx equals 0. Which this equation is called undamped, unforced. So people always tell me, well, you can't really have no dash pot because there's always air resistance, there's always friction, so on and so forth. Well, you can if you have an external force which does just enough to cancel that out, and then you get that equation, which is our undamped free motion, or undamped and unforced. What's that? Ln?
X double prime.
M, that's an M. My pen went a little goofy there. M for mass right there. Mx double prime. Undamped, unforced are the two words I wrote there. Now, it just so happens, if you take a pendulum, this is derived on page 137 of your book. I'm not going to go through the whole derivation. But if theta is the measure of the angle of the pendulum, K is the pendulum constant, which is G over L, where L is the length, and C, again, accounts for the dash pot, you get exactly the same equation. So the movements of a pendulum are exactly the same as the movements of a spring. Absolutely no difference from a mathematical standpoint. They just look different in motion. All right, so now we're going to solve that differential equation. So let's start with the easier situation, the free, undamped motion. Assume we have a spring with neither damping nor an external force. We end up with free, undamped motion, which means mx double prime plus kx equals 0. I'm going to take this equation and I'm going to divide by m. So I'm going to write this as x double prime plus k over mx equals 0. What can you tell me about k and m? What kind of numbers are they? They're constants. More specifically?
They're
What's m stand for? Mass. Mass is always a positive number, correct? What about k? What was k again?
Spring constant.
The spring constant, which is a positive number. K is a positive number. So these are both positive numbers. Since these are both positive numbers, I can take their square root, can't I? So we're going to let omega naught be the square root of k over m. And then this equation becomes x double prime plus omega naught squared x equals 0. Which has a characteristic polynomial of r squared plus omega naught squared equals 0. And what are the solutions to that equation? R squared equals minus omega naught squared. And so when you do square roots, what happens? R equals plus or minus the square root of negative omega naught squared. But you got a negative number under your square root, so that gives you a complex number, and the square root of omega squared is omega. So you end up with complex solutions.
I thought that the W was supposed to represent the Wronskian.
We do use W for Wronskian, but that's a big capital W.
This is a Greek one.
For Wronskian, we use a big capital W. This looks a lot like a W, but it's really supposed to be the Greek letter omega. It's lowercase omega, but when I write it, I make it look just like a W.
Okay.
So.
Larry calls it
The Wegmans.
Tom.
All right, well, the important thing is we get complex solutions. So when we get complex solutions, what happens? You get a cosine and a sine. Okay? Now, I want to go back to this answer that I got here. This one had a dampening factor, so that's why the amplitudes decrease as you go. What's going to happen if it's not damped? The amplitude will stay the same. It'll be a traditional sine or cosine wave. But look at the answer we got. The answer we have has a cosine plus a sine. It's supposed to just be one or the other, isn't it? It should be just a sine wave or just a cosine wave. So the answer turns out to look like that. So now we're going to do some fancy trigonometry to make it look like a sine wave or a cosine wave. Let's see how good our trigonometry is. All right, so we're going to make, remember in our answer had a cosine omega naught t plus b sine omega naught t. We're going to create this new letter. We're going to call it c. C is the square root of a squared plus b squared. What does that look like? It looks just like the Pythagorean theorem, doesn't it? And we're going to let cosine of alpha be a over c and sine of alpha be b over c. How can we do that? We just made a triangle. That's correct. So we're making a triangle. We're calling this alpha. We decided to call the hypotenuse c. Which one's a and which one's b?
Across is B, right next to it is.
Across is b and adjacent is a. Because we want cosine of alpha to be a over c, adjacent over hypotenuse. Sine of alpha to be b over c, opposite over hypotenuse. However, there's a little note here that says, note that alpha is not given by the usual branch of the inverse tangent. So what I'm saying there is I could easily write tangent of alpha equals b over a, opposite over adjacent. So it's very tempting to write that alpha is arc tangent of b over a. Very tempting to write that, but you need to be careful. When you do arc tangent of b over a, you only get angles in very specific quadrants, written in very specific ways. So what's the range of arc tangent? What kind of answers do you get when you use the arc tangent function?
So like,
Isn't it the first and third quadrant?
It is not first and third.
is it between pi over 2 and 3 pi over 2?
No, it's in which ones?
First and fourth.
First and fourth. That's right. When you use the traditional arc tangent function, your range, the answers you get, are in the first and fourth quadrants, but even more specifically, the ones in the fourth quadrant are written as negative values. When you use arc tangent only gives you answers between negative pi over 2 and pi over 2. And that's not sufficient for us because based on what's happening, these A numbers and B numbers, they might be positive and they might be negative. And so we have to be a little bit more careful here. If A and B are both positive, we don't have any issues. Because if A and B are both positive, then my triangle looks exactly like I just drew it. Alpha is in the first quadrant, and so I can just do the arc tangent. Nothing to worry about, because arc tangent will give me answers in the first quadrant. But what happens if A is a negative number? Then my triangle doesn't look like this. What does it look like?
Second quadrant.
It's in the second quadrant, or it's in the, could be in the third if B is negative.
Yeah.
So if A is negative,
Four on the same one is-
if A is negative, then A is going this way. And so if B is a positive number, this is my angle alpha. Actually, my angle alpha would be this one. There's my angle alpha. But that's an angle in the second quadrant. If I use the traditional arctangent button, it's not going to give me an answer in the second quadrant. It's going to give me an answer in which quadrant?
4.
4. Why 4? Because tangent is negative in quadrant 2, so it's going to give me an answer in quadrant 4. So I need to take the answer in quadrant 4 and turn it into an answer in quadrant 2. To do that, you add pi. So if A is a negative number, you do the traditional tangent inverse, but then you have to add pi. The same thing happens if your triangle is actually in quadrant number 3. If A is negative and B is negative, then here's your angle alpha. But remember that tangent is positive in quadrant number 3. So if I push that arctangent button on my calculator, it's going to give me an answer in quadrant 1. And so again, I need to take a quadrant 1 angle and convert it to a quadrant 3 angle, which means I have to add pi. So if A and B are both positive, you're in quadrant 1, no problem, use the regular arctangent. If A is negative, then you're either in quadrants 2 or 3, so when you push that arctangent button on your calculator, you got to add a pi. And finally, if A is positive but B is negative, you're going to get an answer that's in quadrant 4, right? Because A would be over here, B would be down here. But again, when you push that arctangent button, it's going to give you a negative answer, but C can't be a negative number. Or, I mean, alpha can't be a negative number. Alpha's got to be a positive angle. So, to take an angle in quadrant 4 and convert it back to an angle in quadrant 1 that we need, we have to add 2 pi.
2 pi would put it right back where it was. It's a full revolution.
But remember, this angle is going to be written as like negative pi over 6.
Oh, so it's referencing the 2 first.
So I take negative pi over 6 and add 2 pi. You're right, it gives me the exact same angle, but it gives it in terms of a positive value. All right, so now that was some challenging trigonometry. Here comes some more good trigonometry. Now that we have all that set up, our solution was A cosine omega naught t plus B sine omega naught t. I'm going to write A as A over C, and I'm going to write B as B over C. And the penalty for doing that? I got to multiply by C. So there's the C that I'm multiplying by. Then we go back up here. A over C was cosine alpha, and B over C was sine alpha. So instead of my A over C, there's my cosine alpha. And instead of my B over C, there's my sine alpha. And now we have one of our most famous trig formulas. We have cosine something plus sine something. That's cosine of subtract the two somethings. So this becomes the C cosine of subtract the two things. The two things are omega naught t and alpha. So there's the final solution of our answer. X of t is C cosine omega naught t minus alpha. There's how we get our answer written using just one trig function instead of two, instead of sine plus a cosine.
So if sine and cosine were switched around in the original function, we would end up with sine or omega t plus alpha.
If sine and cosine were switched around in the original function, you mean in this one?
Yeah.
Then I would say that I'm adding so I can switch order and I'd put them back the right way.
So it always comes out to be a cosine.
It always comes out to be a cosine function, which of course is really a sine function with simply a different phase shift. That's all.
George, does the cosine mean that you're starting from a max amplitude, whether minus or positive?
No, not necessarily. It depends on the phase shift. Because you're right. Your cosine graph traditionally starts like this and looks like so. But if this number here, this is your phase shift, this moves the graph left or right. So if your phase shift is, say, pi over 2, then your graph would be shifted over and look like that.
What if you had zero phase shift and you started from rest?
If you had zero phase shift, then absolutely your graph is going to start at its highest point or its lowest point if you started by stretching or compressing. If you compressed it, then it would start at its lowest point. If you stretched it, it would start at its highest point. So if you have no phase shift, then yes, it's always going to start at either its peak or its min. But if you started it somewhere in between, or if you started it, this might be you started it in its natural position, but you gave it an initial velocity that was negative. And so it started at rest, but then you pushed it, and so it went down first, and then back up, and then down. So that one would have a phase shift on your cosine graph. All right, now, all these numbers, the C, the omega naught, and the alpha, they all tell us some important things. You might remember from your days in pre-calculus, this number C is called the amplitude. This number omega naught is known as the circular frequency. Alpha is called the phase angle. In pre-calculus, we usually call that the phase shift. So I tend to use those words a lot. I usually call that the phase shift. No, that one's not the phase shift, I'm sorry. This one's the phase shift down here. The period. The period of cosine is normally 2 pi, but since we have this omega, our period is going to be changed. So the period is going to be 2 pi over whatever that omega naught number is. Frequency is the reciprocal of period. So once you know the frequency, once you know the period, you know the frequency. And this number, you take the alpha and you divide it by the omega naught. That's normally called your phase shift in pre-calculus. Here we call it the time lag. I don't know why they use the term time lag, but they do. Questions? How do you do problems with this? Excellent question. So this is section 2.4. Number 2. It says, determine the period and frequency of the simple harmonic motion of a body with a mass of 0.75 kilograms on the end of a spring with a spring constant of 48 newtons per meter. All right, so looking back at my notes here, how do I find the period? 2 pi over omega naught. And once I know the period, the second part, the frequency, is already done, isn't it? So our period is 2 pi divided by omega naught. So what was omega naught? Omega naught was the square root of the spring constant over the mass. So the answer is 2 pi divided by the square root of the spring constant, which is 48, divided by the mass, which is 0.75. That's 2 pi over. What's 48 divided by 0.75? I'm guessing it's 64. Yes? Why did I guess 64? Because if I'm dividing by 3/4, that means I add a quarter. Or my other guess was that I took the next perfect square that was above 48, hoping the numbers worked out nice. That was really what I did. I wasn't thinking that far ahead. So that's 2 pi over 8, so that's pi over 4. So the period is pi over 4, which means the frequency is 1 over that. 4 over pi. Questions on that one? Ah, that one was easy, right? Always start you off with an easy one, make you feel good. Number 4 says, a body with a mass of 250 grams is attached to the end of a spring that is stretched 25 centimeters by a force of 9 newtons. So we have X equals 25 centimeters when the force is 9 newtons. At time equals 0, the body is pulled 1 meter to the right. So that would be X. X is my distance. And, well, I assumed right was stretching, but it does say stretching the spring. And set in motion with an initial velocity of 5 meters per second to the left. So that would be X prime is 5 meters per second to the left, which means it's negative, isn't it? Because stretching it was to the right, that was positive. If I'm pushing it to the left, that's negative. The directions are find x of t. So it wants us to find x of t in the form c cosine omega naught t minus alpha. And then it says find the amplitude and the period. Well, once I have this formula written out, I can very easily find the amplitude and the period, correct? All right. What do you do? We know how to find omega naught, don't we?
Well, that's K over M. But we don't have the
Omega naught is the square root of k over m.
That's converted kilograms as well.
Absolutely, you need to be very careful. Since this was given in newtons, this distance has to be in meters, and that mass needs to be in kilograms. All right, so be very careful of that. Your author loves doing that. He loves mixing around the units on you. And he likes throwing in hyperbolics in the homeworks just for fun too. All right, so that one's 0.25 kilograms, and this one is 0.25 meters.
K would be the 9 over the 0.25 meters.
Okay, that's right. So K, we know that F equals Kx. So plugging in those initial conditions, we know 9 equals K times 0.25, which means K is 36. So omega naught is the square root of K, which was 36, divided by 0.25. Let's see, that's going to be 6 divided by a half. That's 12, maybe?
Yeah,
12? So omega naught is 12. Well, knowing simply that information, knowing that omega naught is 12, I can already answer part B. Part B was find the period, find the frequency. Period is 2 pi over 12, which is pi over 6. And the frequency is the reciprocal of that, which would be 6 over pi. So there's the answer to part B. Part B is the easy part. All right, so now the big question is, how do I find C and how do I find alpha? How is C defined again? It turns out to be the amplitude. That's correct. I don't think so.
It's the restoring force.
No, this is capital C, not little c. Be careful there. C was defined as the square root of a squared plus b squared, where a and b came from having your solution written in this form. A cosine 12t plus b sine 12t. So in order to figure out C, I really first need to figure out A and B. How am I going to figure out A and B? Do some factoring? No factoring. I could use a matrix. I don't think I'm going to need a matrix. More specifically, what I think I'm going to do, I'm going to take those initial conditions and I'm going to plug them in. That's how we always find, usually we call these C1 and C2. That's how we always find those two constants. We plug in our initial conditions. So when t equals 0, x is 1. So that means 1 equals, what's the cosine of 0? 1, so this is just A, plus what's the sine of 0? 0, so A is 1. Hey, that was nice. Then I got to take the derivative, plug in my derivative, so x prime at t is negative 12a sine 12t plus 12b cosine 12t. I plug in this number. So negative 5 equals, when I plug in 0, sine of 0 is still 0, cosine of 0 is still 1, so I get 12b there. So b is minus 5/12. Why is the t still the same? Not sure what you mean. All I did is I took the derivative. The derivative of cosine 12t is sine 12t. But I got to multiply by the 12. And then the two initial conditions both had t equals 0.
Oh, okay.
So I plugged in 0, t equals 0 for this equation and for that equation.
Oh.
Okay. All right, so now we can find C. C is the square root of 1 plus 25 over 144, which is square root of 169 over 144, which is 13/12. Oh, and it did in part B ask me to find the amplitude. Well, there it is. Amplitude is 13/12. Almost done. What's the last thing I have to do? I have to find alpha. And so we need to go back and look and remember how alpha worked. There was my sheet. Here it is. Let's see. In our case, A is a positive number. A is 1, but B is a negative number. When A is a positive number and B is a negative number, alpha is 2 pi plus the arc tangent of B over A. So I'm kind of running out of room here. Alpha, squeeze it in down here, is 2 pi plus the arc tangent of B over A. Negative 5/12 over 1. And I think it would probably be reasonable to get a decimal approximation for that. am in radian moles, that's good. 2 pi plus the arctangent of negative 5 over 12. Alpha is about, we'll call it 5.89. Final answer then. X of t is, my C number was 13/12. Cosine of omega was 12t minus 5.89. Questions on that?